Hello and welcome to lesson number 5, circular functions. So, to talk about these, we need to first talk about the unit circle. The unit circle is a circle of radius 1 that is centered at the origin of the coordinate plane. We talked about this in the last video, so this should be familiar to you. In the Cartesian plane, if we take the origin and we draw a circle of radius 1 around it, that's what we call the unit circle. Now, considering the points on the unit circle, if I draw a line at an angle theta to the x-axis along the unit circle, cutting it like this point of intersection is a distance of 1 away from the origin. Let's also consider the coordinates of this point. So we know this hypotenuse of this right triangle which I am about to draw here is 1. And we know the base of this right triangle is along the x-axis and the height of this right triangle is along the y-axis. So, the distance that we will travel from the origin in the x direction, or the abscissa of this point, is this length, and the ordinate or distance we will travel along the y-axis of this point is this. So we have the ordinate here and the abscissa here, and we can find them by trigonometry. But in order to do that, we need to first define certain functions. For a right angle triangle, which I am going to draw here, and I am going to generally call an angle theta here, this longest side, the side opposite to the 90 degrees on the right angle triangle, is what we call the hypotenuse, which I am going to label with a simple h. It's the longest side of the right angle triangle. The side that is opposite to the angle theta is what we call the opposite side, and usually denoted by O. And the side that is not the hypotenuse and not the opposite side is what we call the adjacent side. So it's written with a simple A for adjacent. So this side here is the adjacent side. Given this setup in this triangle, sine of theta is defined as the opposite divided by the hypotenuse. And because for any triangle, in right angle triangle, having an angle theta, all of them will be similar to each other. For example, if I have another triangle, another right angle triangle of different size with 90 degrees here and theta here, this angle here will also be the same as this angle. So all three angles of this triangle are the same, meaning that this triangle, the small one and the large one, are both similar triangles, which means the ratio of this side to this side will be the same as in the large triangle. So actually, the value of sine theta is independent of the actual size of the triangle. Any triangle with an angle any right angle triangle with an angle theta will have sine theta equal to this. Similarly, another trigonometric function cos theta is defined. Cos theta is defined as the adjacent side divided by the hypotenuse, and another function which we call tan theta is defined as the opposite side divided by the adjacent side, which you can see from the other two is actually sine theta divided by cos theta. If you divide sine theta by cos theta, you get O divided by H divided by A divided by H. The divided by H is cut and we just get O divided by A. So we have tan theta is equal to sine theta divided by cos theta. These are the three main trigonometric functions. Some people might tell you that there's actually 6 main trigonometric functions, and those people are madmen. The other three trigonometric functions they're talking about are, if I just line them up, sine theta, cos theta and tan theta are the ones we just talked about, these three ratios. The other three that those people are probably talking about are cosec theta, sec theta, and cot theta. Sine theta is opposite divided by hypotenuse, cos theta is adjacent divided by hypotenuse, and tan theta is opposite divided by adjacent. These other three that these people talk about are cosec, sec, and cot, which are hypotenuse divided by opposite, hypotenuse divided by adjacent, and adjacent divided by opposite. They are literally just the inverses of the others. 1 over sine is cosec, 1 over cos is sec, and 1 over tan is cot. They do have their own somewhat unique behavior, like making them at least warrantable as being separate functions, but I for one do not agree with this. I prefer sine, cos and tan, and prefer to exclude cosec, sec and cot. So now that we have sine, cos, tan and the other three, and we know that these are independent of a triangle, and for any right angle triangle, sine of theta is simply the opposite side divided by the hypotenuse, and cos of theta is simply the adjacent divided by the hypotenuse, and tan of theta is simply opposite divided by adjacent. Let's now apply that to this triangle which we have drawn here. Considering this triangle, the base length and the height are what we want to find, but we know the hypotenuse. So for this particular triangle, if I write sine theta is whatever length this is divided by 1. If I call this point, we'll say this point is P and this temporary point is Q here, then PQ is sine if we write PQ divided by 1, that would be sine theta, because sine theta is the opposite side divided by the hypotenuse. So PQ divided by 1 is sine theta. So PQ is sine theta times 1, which is just sine theta. So PQ is sine theta. Similarly, OQ, in this case, OQ divided by 1 is cos theta, because cos theta is adjacent side divided by hypotenuse. So in this case, OQ is 1 times cos theta or simply cos theta. So we have OQ equals cos theta. So PQ equals sine theta and OQ equals cos theta. Now recall what I said, that the coordinates of P can be found by the x distance you have to travel and the y distance you have to travel from the origin to get to P. So in order to get to P, we need to travel OQ distance horizontally and QP distance vertically. That means that the coordinates of P are the x distance traveled, which is cos theta, comma the y distance traveled, which is sine theta. So this point P is cos theta, which is the abscissa, comma sine theta, which is the ordinate. This is the equation for the coordinates of the point P. Regardless of what the angle theta is, the coordinates of P are cos theta, comma sine theta, based on this trigonometric relationship that we have found. So we have found the point P. Now you'll note an interesting thing. From earlier, we can actually prove this separately also, but you'll note, if we take the distance OP, from the previous lesson we know the distance of any point to the origin is simply its x coordinate squared plus its y coordinate squared. So OP is really the square root of cosine squared theta plus sine squared theta, which we also know is equal to 1 because OP is a radius of the circle that we drew earlier, which is the unit circle. So we know that the square root of cosine squared theta plus sine squared theta is 1, which then leads us to know that cos squared theta plus sine squared theta is equal to 1 squared is equal to 1. Meaning that sine squared theta plus cosine squared theta is equal to 1. This is actually true for all angles of theta, and we can somewhat show that this is true by considering certain cases and drawing certain triangles. We're not going to really do that. If you want, I'll make a proof of that and link it up in the top right, and we can discuss that. But there is one trigonometric relationship that we must know when we're talking about any trigonometry. We need to know this relationship, the fact that for any angle theta, I'll write that on the side as well, for any theta, for now we'll just say element of real numbers, for any theta, sine squared theta plus cosine squared theta of that theta is equal to 1. Next, we have shown in this circle sine theta and cosine theta. What about this other length that I have shown here? What's this tan theta? This ratio tan theta, where can we find it? Well, you can actually get a hint from the name of the function. The name of the function is tan theta or tangent of theta. So, tangent. A tangent to a circle is a line that touches the circle at exactly one point. It is perpendicular to the radius of the circle at that point, like this. This is perpendicular and it touches the circle at only one point. The tangent of theta is actually this length. this length from the point P like this down to this point here, which I'll call R, and I'll prove to you that this PR length is in fact the ratio of opposite to adjacent. So if I draw this triangle, and I'll also denote this angle is 90 degrees here. OP to PR angle is 90 degrees because PR is a tangent to the circle. Considering the triangle OPR, if I consider triangle OPR and I draw it separately, OPR, if I draw it separately, we have this triangle here, horizontal line here, a line like this and a line like this, line like that. We'll erase the excess of this because it's nice that way. Now we have this triangle. In this triangle, this point here is the origin. This was theta, this point was P, this point was R, and this was 90 degrees. All correct? All correct. And we knew that this side length was 1. The side length over here was 1. That's all we knew. So here, if we consider the ratio of tan theta is opposite divided by adjacent, I said. So in this case, tan theta is PR divided by 1. Well, what do you know? If we take this 1 to the other side, we get that PR is equal to 1 times tan theta, which is just tan theta. So PR, this line's length, is tan theta. So here, the line's length from here to here is tan theta. Now we can actually find the other trigonometric relationships in this circle also. I'm not going to do that again. I will post another video. It will be up in the top right. You can click the link where you can watch how the other 3 trigonometric ratios, the inverses of the first 3 functions, these 3 can also be found within the same unit circle. Continuing on topic, however, if we consider these 3 functions, sine theta, cos theta and tan theta, these 3 functions have certain domains and certain ranges. Let's consider those domains and ranges. If you talk about this sine theta, cos theta and tan theta, considering the triangle here, we can see that sine theta is anywhere between this height and this height. Why is that? Well, recall that the y-coordinate of the point P is sine theta. And note that because we have a unit circle and that P is on the unit circle, P can only be wherever the unit circle can be. And the unit circle is confined to this region which we have drawn here. The maximum point of the y-coordinate of P is at this point here, which I have highlighted. This point is the point at which y equal to 1 and also x equal to 0 at this point. And the minimum point of y on this circle is this point here. At this point, x is equal to 0 still because we have not gone anywhere horizontally relative to the origin. But now y is equal to negative 1 because we have gone down a radius downward in the negative y direction and the radius is 1. So this means that sine theta can only be between 1 and negative 1. And note that it is inclusive because the point here x0, y1 is a valid point on the circle. Similarly, the other point on the bottom, x0, y negative 1 is a valid point. So if we talk about sine theta, if we go down here, I'm going to go down here. I'm going to break the page into 3. Here we're going to talk about sine theta. Here we're going to talk about cos theta. Here we're going to talk about tan theta. For sine theta's range, the possible values of sine theta is between negative 1 and 1 inclusive. Recall the square brackets mean inclusiveness. So sine theta can be negative 1, can be 1, can be anywhere in between but cannot be outside negative 1 and 1. Next, if we consider cosine theta. Cosine theta is the x-coordinate of the point P. And note that point P can also go anywhere on the circle and the maximum value of x for the point P is found at this point. This point here, at this point x is equal to 1 but y is equal to 0. We've gone a radius distance along the positive x direction at this point and nowhere in the y direction. And similarly, the minimum point of x is at this point here. At this point x is equal to negative 1 and y is equal to 0. We've gone a radius distance of 1 in the negative x direction and nowhere in the y direction. So because the x coordinate of this point P is cosine theta, we can see that cosine theta is limited again between negative 1 and 1. So the range of cosine theta, range for cosine theta is also limited between negative 1 and 1. Again inclusive because the two the extreme points are included in cos theta as well as sine theta. How about tan theta? Where can tan theta go? Well, for that we'll draw a separate diagram and try to figure it out. If we draw another circle and we consider the possible tangent values it can have, the possible lengths of the tangent to the circle touching x-axis, like this and like this. If we extend this and consider the possible values, when theta is very small, approaching 0. If theta is very small, approaching 0, the tangent length from here down to here is also very small. In fact, as we get a smaller and smaller angle theta, as theta goes to 0, we can see the tangent appears to be disappearing. It appears to get really small and go to 0. So in fact, tan theta can be 0, no problem. As we make the angle bigger, tan theta also gets bigger. We can easily see this if we just make the angle bigger. If I consider the angle something like, let's say, that. Now the tangent of theta is this long, so it gets bigger. If I make the angle very close to 90, we can see that the line here is getting flatter and flatter and getting longer and longer. If I make the angle almost equal to 90, meaning almost vertical, very slight curvature, slight non-verticalness, then the line here is going to be going for a very long time. Excuse me, I cannot easily draw flat lines here. Let me try to approximate one. There we go. So this line here is going for a very long distance before it meets this other line on the x-axis. But it will eventually meet the x-axis somewhere very far away. However, if the angle here, the angle to the center, this angle is exactly 90 degrees over here, this angle is exactly 90 degrees, then the tangent here would actually be parallel in direction to the x-axis. These two lines would be parallel. And as we know, parallel lines do not meet, which means that theoretically if it did meet, it would meet at infinity. The parallel line would converge the other line at infinity. Which means at this point, the tangent value of theta approaches positive infinity. But look at the other direction. If we extend this line in the other direction, and we think about where it's connecting on the other side, since these two lines are also parallel, there would be a connection on the other side. In fact, if we make theta, this angle theta, a little bit larger than 90 degrees, then we can see, if I just quickly erase this, make this angle a little bit larger than 90 degrees, something like, say this. Now we can see, drawing this tangent, it is intersecting the axis in the negative direction. In the negative x direction, there is an intersection. So that means that if we break the angle close to 90 degrees from the other side, if we have an angle greater than 90 degrees and we decrease it, then our tangent of theta is approaching an infinity from a different direction. So in fact, if you draw the graph of tangent of theta, you will see this, which we will do really quickly. if we consider the origin, the 0, 0 point or origin here, this is the y-axis and that's the x-axis. Then the graph of tan theta will look like this. It will go up, it will slow down a little bit and go up, up, up really fast. It will go really fast. This is what I meant by going to infinity. This angle right here is 90 degrees. At exactly 90 degrees, the two lines, the line of tangent and the x-axis are parallel to each other, which means that they will never reach, or the distance required for them to reach would go to infinity. On the other side, you would actually see a line coming from negative infinity upward like this and going like this. And the reason for that is, for angles greater than 90 degrees like this, if I just draw on this diagram, angle greater than 90 degrees, the x-coordinate of this point is negative, but the y-coordinate is positive. So that means we have cosine theta, sine theta which is positive, but a cosine theta which is negative. Since tan theta is equal to sine theta divided by cos theta, if sine theta is positive but cos theta is negative, a positive number divided by a negative number will give us a negative number, which gives us that tan theta will be negative for little small angles slightly greater than 90 degrees. Hence the approaching from negative infinity on this side. And yes, I know this is somewhat counterintuitive. If we define the length of the tangent as tan theta, shouldn't the length always be positive? And yes, you are correct. But that's because that's not exactly how we define tan theta. Tan theta for angles less than 90 degrees is exactly equal to the length of the tangent. For angles between 90 and 180 degrees, it's equal to the negative length of the tangent. And yes, there's a little bit of confusion there, but I apologize, that simply cannot be reconciled. The tan theta is not defined as the length of the tangent. It only happens to be the length of the tangent exactly when the angle is between 0 and 90, and also between 180 and 270, which we will talk about later. But for now, note that tan theta can go anywhere from positive infinity to negative infinity, which means that the range of tan theta is from positive infinity to negative infinity. Range of tan theta is positive infinity to negative infinity. So negative infinity, comma positive infinity. Note that when we write infinity in a range, we do not include infinity itself. It is a non-included value, which is why there's a curly brackets, there's curved brackets in the range equation here. Range equals starting from negative infinity non-inclusive, ending at positive infinity non-inclusive. Next, if we talk about the domain. If we talk about the domain for these three trigonometric functions, we are putting an angle into here. So the angle could start at 0, and we could start turning in the anti-clockwise direction and start taking angles. We could take this angle, it's valid. We could take this angle, it's valid. We could take a bigger angle like this, it's valid. We could do a full circle and come all the way back, it's valid. And actually, we could do more than a full circle, something like this, and come all the way back to here. In fact, we can do this infinitely many times. We can spin as many times as we want around this origin like this. We can spin as many times as we want and come back and stop. So the angle in the positive direction can get as big as it wants. How about in the negative direction? Well, going for an angle in the negative direction still makes sense. This angle is also valid. If we go clockwise, counting that angle, it is still a valid angle. So that's also alright. Similarly, we in the negative direction, we can go as many times as we want in a circle before stopping. We can go as many times as we want and then stop. What does this mean? This means that the angle can also be anywhere in the negative direction and still end up pointing in the same final direction. No, remember, angle is simply how much you have to rotate in order to get to looking in a certain direction from a certain different direction. Starting from this direction, in order to look in this direction, there's many different ways that you could do it. So here, the angle theta that we input into sine, cosine and tangent could be any real number. It could be any negative number, any positive number, anything as big or small as needed. So, the domain of these three functions, the domain of sine theta is the real numbers. The domain of cosine theta is the real numbers. And the domain of tan theta is the real numbers, except for points where we get an infinity, because technically speaking we do not really want to include infinities, infinities and divide by zeros into our domain. The reason for this, the reason that I say there's a divide by zero, is because what happens at 90 degrees and its multiples is that cosine theta becomes 0. We can easily see this if we consider the unit circle. The x-axis coordinate is cosine theta, and cosine theta is 0 at this point here. X is 0 at this point and this point. And these points occur when we have 90 degrees times some multiple of 180 degrees. You'll note 90 degrees plus some multiple of 180 degrees, if we write that in radians, it is pi by 2 radians plus some multiple of pi. So when we have pi by 2 plus 0 times pi, if we take n here, pi by 2 times 0 times pi, pi by 2 plus 1 times pi, pi by 2 plus 2 times pi, all of them will get us either to this position or this position. And in these two positions, x coordinate of our point is 0, which means the cosine value of our point is 0, which means that we are having a divide by 0 in tan theta. So to eliminate this, to eliminate getting to this point or getting to this point, we simply remove those two from the domain of tan theta. So we say that tan theta is the domain of the real numbers minus all the numbers that are pi by 2 plus n times pi, where n is an integer. All the integer multiples of pi plus pi by 2, we want to get rid of those from the domain R. Note that here this subtraction that's happening, here is a set subtraction. We are removing all the values of pi by 2 plus n pi for n in the integers out of the real numbers set. So now that we've established that, before going to the actual values of sine, cosine and tangent, let's talk about some interesting symmetries and repetitions that occur within sine, cosine and tangent. And to do that, let's just consider this thing right here. The coordinates of this point are cosine theta, sine theta. The x coordinate is cosine theta, the y coordinate is sine theta. Similarly, the length of this tangent here is tan theta. If I do a full circle, and I come back to this point, the angle of this thing would be 2 pi plus theta, because I have traveled a full circle of 2 pi radians and an additional theta in order to do that full circle and get all the way back to the same direction. Whether I rotate pi radians around the circle or theta radians around the circle or 2 pi plus theta radians around the circle, I am still facing the same direction here. So what this means is that cosine of 2 pi plus theta, sine of 2 pi plus theta is the exact same point, as cos theta, sine theta, because I did the rotation, right? I did the rotation and I came back to the same exact point, which means that cosine of theta has to be equal to cosine of 2 pi plus theta, and similarly sine theta has to be equal to sine of 2 pi plus theta. What this means is that rotating a full circle and coming back to the same point did nothing to sine theta cos theta. And since tan theta is sine theta divided by cos theta, we can also say tan theta is also equal to tan of 2 pi plus theta. Because rotating an extra 2 pi radians, rotating an extra full circle did nothing to our values. Sine theta, cos theta and tan theta are all the same. So we'll mark this with a star. This is our first relationship of repetitive symmetry. Every 2 pi radians, every full rotation of a circle, the value of sine theta, cos theta and tan theta repeat and become the exact same. So that's one repetition we'll consider. Next, let's consider, instead of a full circle of 2 pi radians, what happens if you rotate only half a circle around the circle. So to do that, we will now draw another diagram and consider a rotation of pi radians or half a circle around the circle. Alright, so here it is. This point that I've drawn here is cos theta comma sine theta, and the other point on the other side here, this point is cos theta plus pi angle comma sine theta plus pi angle. We have traveled an extra pi radians around the circle like this. So now let's consider the properties of this point. At this point, we have turned a full 180 degrees around the circle, a full pi radians around the circle, and we can see some interesting symmetries happening. If I draw this line like this, you can see this distance here and this distance here are equal, this distance here and this distance here are equal. However, they are now in opposite directions. This and this are in opposite directions, and this are in opposite directions. What does this mean for us? It means that the cosine value and sine value of this second point are exactly opposite, are negative of the original sine and cosine values. So what does this mean? This means that cosine of theta is equal to negative cosine of theta plus pi radians, theta plus pi radians. Similarly, sine of theta is equal to negative sine of theta plus pi radians. And also, because tan theta is sine theta divided by cos theta, and we have negative sign on both of these actually cut when we divide, and taking that, tan of theta plus pi would equal sine of theta plus pi divided by cos of theta plus pi, which is sine theta divided by cos theta, negative sine theta divided by negative cos theta. Cutting the two negatives, this would simply be sine theta divided by cos theta, which is tan theta. So actually, tan of theta plus pi is equal to tan of theta. It's a simple, nice relation. Tangent value does not change when you rotate a full half a circle around the circle, but sine and cosine become negative. So this is another second repetitive relationship. It's not the same because two of them are changing, but tan theta is still remaining the same. And the other two that change have a nice change. It's simply multiplication by -1. If you go half a circle around the circle, sine theta becomes negative sine theta, cos theta becomes negative cos theta. We have a multiplication of -1 for these two. Next, let's consider rotations of 90 degrees in both the positive and negative directions. And note that the rotation of 90 degrees in the negative direction will be considered as a rotation of positive 360 minus 90 degrees in the positive direction. Alright, the construction is a little bit messy, but bear with me. Here we have the point cos theta comma sine theta drawn here normally. It's at an angle theta relative to the x-axis. We have another point which is rotated an extra 90 degrees here. We have another point that's rotated negative 90 degrees from this current location, which is the equivalent of rotating it by positive 270 degrees in this location. So I've drawn actually the positive rotation one, but note that a positive rotation of 270 degrees is equal to a negative rotation of 90 degrees. Now, let's try and figure out what's happening here. If we consider this angle, since this is 90 degrees, we have theta plus some angle is equal to, we have theta plus some angle is equal to 90 degrees. So, this angle should be 90 degrees minus theta. So this angle here is 90 degrees minus theta, or pi by 2 radians minus theta, and because of that this angle here is theta. Similarly, on this side, if we do the same exact thing, this is theta, this is 90 minus theta, which means this angle here would also be theta. Now let's try and use this to figure out the coordinates of those other points. If I erase this thing just to get us a little space, note that this is a radius of the circle. This length here to here is a radius of the circle, so this is 1. This length here is also 1. Considering that, we have theta here, which means this length here, if we consider the relationship, this is the opposite side, this is the hypotenuse, so that length here would be the hypotenuse times cosine of theta, which is simply cosine of theta. So this direction here, this length is cosine of theta. How about this side? On this side, this length in this direction would be sine of theta. So we have, if I draw this triangle separately, we have the triangle here, 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 and here, where this is length 1, this is length sine theta, and this length is cosine theta. So, to get to this point, we had to go a positive distance of sine theta and a negative distance of cosine theta. So this is a negative distance, this is a positive distance. Which means that the point here, the point that we are considering here, is in the positive sine theta and in the negative y direction cosine theta. So, considering this is equivalent to this, which means that cosine of theta plus 3 pi by 2 or 270 degrees is equal to sine of theta. Note also that because a positive angle of 3 pi by 2 or 270 degrees is equivalent to a negative angle of 90 degrees, this is also equivalent to cosine of theta minus 90 degrees. Rotation of minus 90 degrees is equivalent to a rotation of plus 270 degrees. Similarly, considering the sine of theta plus 3 pi by 2, it is equal to negative cosine of theta. So negative cosine of theta is equal to, again, sine of theta minus pi by 2. The reason for this is that rotating in the negative direction by pi by 2 is equivalent to rotating in the positive direction by 3 pi by 2. Now if we consider tan theta in this situation, I'm actually going to take a little bit of effort to write it out because it's a little counterintuitive. Tan theta plus 3 pi by 2 is equal to sine theta plus 3 pi by 2 divided by cos theta by 3 pi by 2. Sine theta plus 3 pi by 2 divided by cos theta plus 3 pi by 2. So what are these equal to? Sine theta plus 3 pi by 2 is equal to negative cos theta, and cos theta plus 3 pi by 2 is equal to sine theta. So this is also equal to negative 1 divided by sine theta divided by cos theta. So therefore tan of theta plus 3 pi by 2 is equal to negative 1 over sine theta divided by cos theta is tan theta, therefore it's equal to negative 1 over tan theta. So we have another interesting relationship. I'm going to move this scratch work away a little bit to make room for our actual conclusion. Our actual conclusion here is that tan theta plus 3 pi by 2 is equal to negative 1 over tan theta. An interesting conclusion, and that will do us for this third point, this third repetitive symmetry, which I will label with a star. Let's move on to the other case, not the minus 90 case, but rather the plus 90 case. If we go for the plus 90 case here, going for this point, again we can see we have this triangle here. In this triangle has a hypotenuse of 1, and if we take this length here is sine theta, and this length, if we take this length, it is cosine theta. So drawing this triangle out in a separate diagram, if we do that, we can see this is the origin going up and left. If we consider going left part and draw this thing, this is the point that we're interested in. This is the origin. This was theta, this was 1. We went up by cosine theta, and we went in the left side by sine theta. So the coordinates of this point are positive cosine theta in the y direction and negative sine theta in the x direction. So we write that first, negative sine theta in the x direction, comma cosine theta in the y direction. So recall, because of our rotation, this point is also equal to cosine theta plus 90, comma sine theta plus 90. So we have the relationship that this point is also equivalent to cosine theta plus 90, comma sine theta plus 90. So cosine theta plus 90 is equal to negative sine theta, and sine theta plus 90 is equivalent to cosine theta. Now again we have, it looks almost the same as the previous one, except the minus sign has changed locations. Previously in the other case minus sign was here. Now if we consider tan theta in this case, I will not do the same scratch work here. I'll just say tan theta plus pi by 2 is equal to sine theta plus pi by 2 divided by cos theta plus pi by 2, which is cos theta divided by negative sine theta is again equal to negative 1 over tan theta. So again we have that tan theta plus pi by 2 is equal to negative 1 over tan theta, and this is to be expected, of course, because the 2 points that we were considering here, this point and this point, were 180 degrees apart. You can clearly see they were 180 degrees apart. And recall our very first symmetry that we found, when the 2 points are 180 degrees apart, tan theta remains unchanged. So it shouldn't be surprised by the fact that for this first point tan theta was negative 1, tan theta plus 3 pi by 2 was equal to negative 1 over tan theta, and for the second point it was also the same value, because anyway those 2 points were 180 degrees apart, as we can see here. This point and this point are 180 degrees apart. So we have that. That is our fourth conclusion, that if we add 90 we get this. Now we are actually not done. There's a couple more interesting ones for us to explore. These are all the adding angles and doing something and seeing what happens. If you recall, we added 90 degrees. We took our point here, we added 90 degrees like this. Then we added another 90 degrees to get us to 180 degrees like this. Then we added another 90 degrees to get us to 270 degrees like this. And that last one, that last addition of 90 degrees could also be considered as an addition of negative 90 degrees to get us to that position again. Now, what we will consider next is what happens when you subtract angles from them and what kind of values do you get. It's quite interesting, and let's quickly, I'll draw it and we'll get to that. Alright, so I've drawn out the circle that we require. This is it. And we have the angle theta that we want to find. And we have the other angle. And if I mark this as the x-axis, we know the point, this. We know this point. This is cos theta comma sine theta. I've intentionally drawn the angle theta to be small here so that it will be easier to illustrate. It will be easy to illustrate what I want to show. So this is the angle theta, and what I want to find is the angle 90 minus theta. If I want to find 90 minus theta, I can consider the angle 90 degrees, which is this rotation here, and then I can do an inverse rotation of theta degrees. So I can do this. So going to here and then going to here, that means that this line is the line pointing in a direction of 90 degrees minus theta. So this point is the point corresponding to cosine of 90 degrees minus theta, comma sine of 90 degrees minus theta. So now, if we consider this point right here, there's some interesting relationships we can find. If I draw this triangle like this and mark this radius as 1, this is also 1 of course, and consider the relationships drawn in this triangle. This is the origin. Going from the origin upward to here, what is this length? Well, the hypotenuse is 1. The side that we're interested in here is the adjacent side. Therefore, this length has to be cosine of theta. How about this length? Well, the triangle has hypotenuse of 1. This length is the opposite length to this angle theta. That means that this length should be sine theta. Therefore, this point, since both of these are in the positive x and y directions, we can say that that point is also equal to sine theta, cosine theta. The x coordinate, the x distance is sine theta, the y distance is cos theta, so the point here is sine theta, cos theta. Therefore, if these two points are equivalent to each other, then we can say that cosine of pi by 2 minus theta is equal to, and this side we have sine theta. So that means that cosine of pi by 2 minus theta is equal to sine theta. Similarly, sine of pi by 2 90 degrees minus theta is equal to cosine theta. Now isn't that interesting? If you take 90 minus theta, cos of 90 minus theta is sine theta and sine of 90 minus theta is cos theta. They've essentially swapped each other. So what do you think tan of this angle would be? Tan of 90 minus theta would be sine 90 minus theta divided by cos 90 minus theta, which would be cos theta divided by sine theta, which would be 1 over sine theta divided by cos theta, which would be 1 over tan theta. So tan pi by 2 minus theta is equal to 1 over tan theta is equal to cot theta, but I'm not going to give it the dignity of writing it like that. Tan pi by 2 minus theta is 1 over tan theta. So we could actually go for the rest and go what happens when you subtract 100 from theta, what happens, pi from theta, 180 degrees from theta, like all of that we could do that. And what I'm talking about here is what happens to pi minus theta, what happens to 3 pi by 2 minus theta, and so on. But we actually do not need to do that. And the reason for that is this angle is really pi by 2 minus theta plus pi by 2. And we already found out what happens when you add pi by 2 to an angle. So we don't need to do this. This other angle is simply pi by 2 minus theta plus pi. And we already found out what happens when you add pi. So we really don't need to do this. So I'm actually not going to cover these because it's not necessary. If you want, you can try and see what kind of results you get. But since those transformations are essentially this transformation here, this pi by 2 minus theta transformation, plus another offset which we have already covered, I will not be covering them. Instead, we will be covering just one more and ending at that point. The last one we are going to cover is the negative angle relationship. Considering the final relationship, if we consider this circle here, if we consider the angle theta in the positive direction, and then we consider the angle theta in the negative direction, such as this point here is cosine theta comma sine theta. And to get to this other point, what we have to do is go forward a certain distance and go down a certain distance. If I draw this triangle, it will be clear. Since this radius is 1, we have to go forward a distance of cosine theta and go down a distance of sine theta. Therefore, this point here is positive cosine theta, comma negative sine theta. So here we can see that cosine of negative theta, give me a second, cosine of negative theta is equal to cosine of theta, but sine of negative theta is equal to sine of theta. This means that tan of negative theta would be sine of negative theta divided by cosine of negative theta, which would then be negative sine theta divided by cosine theta, which would then be negative tan theta. Negative tan theta. I apologize for a few seconds. I had not written the negative sign here. My apologies for that. Sine of negative theta is negative sine theta. And that also gives us the tan of negative theta is negative tan theta. This is the final relationship that we will be considering. These relationships are often quite handy in examinations. Oftentimes you will have tan of something plus something, sine of something plus something, and very often that angle will be pi or pi by 2 or 2 pi or some multiple of pi by 2, in which case you now have the tool to quickly and easily convert that into simply sine of theta, cos of theta or tan of theta as you require. As a final note, we will be considering the 4 quadrants in sine theta, cos theta, tan theta. The 4 quadrants being this quadrant, this quadrant, this quadrant and this quadrant, which I will explain. And we will also be considering the shape of the graphs of sine theta, cos theta and tan theta. We will not be going into much exacts. We will just be going into special and important points only. So, in the xy plane, considering this as the origin, the quadrant where x is positive and y is positive is the quadrant which we call the first quadrant. This is the first quadrant. In the first quadrant, since x is positive and y is positive, sine theta is positive and cosine theta is positive. Due to this property, tan theta is also positive. Because of this, we say that in the first quadrant, all of the 3 trigonometric functions are positive, or simply all are positive. Sine theta is positive in the first quadrant, cosine theta is positive in the first quadrant, and tan theta is positive in the first quadrant. Note that within the first quadrant, the angle theta is between 0 degrees and 90 degrees. So the first quadrant is the angles 0 degrees up to 90 degrees, non-inclusive. The next quadrant over in the anticlockwise rotation is what we call the second quadrant. Second quadrant. In the second quadrant, the x-coordinate is negative. Y-coordinate is still positive, however. Because the x-coordinate is negative, cosine theta is negative in this quadrant. However, because the y-coordinate is still positive, sine theta is positive in this quadrant. Tan theta is sine theta divided by cos theta. So tan theta is a positive number divided by a negative number, which is a negative number. Within this quadrant, the only positive one is sine theta. So we say within this quadrant, sine theta is positive. And we imply that the rest are negative. It's a common thing that people do to remember where we have positive sine theta, positive cos theta, positive tan theta and such. In the second quadrant, only sine theta out of these three trigonometric functions is positive. Considering the next quadrant, this quadrant you can probably guess is called the third quadrant. Within this quadrant, x and y are both negative. So the x direction we are going in the negative direction, y direction we are going in the negative direction. So x and y are both negative, which means that sine theta is negative and cosine theta is negative. But because tan theta is sine theta divided by cos theta, which is a negative number divided by a negative number, tan theta is actually a positive number within this quadrant. So within this quadrant, the only positive one is tan theta. So we say that tan theta is positive, or just simply we say in the third quadrant tan theta is the one. Which one? The one that's positive. And finally, within this fourth quadrant over here, fourth quadrant, within this quadrant, we are going in the positive x direction, but we are still going in the negative y direction. Positive x direction means cosine theta is positive, but negative y direction means sine theta is negative. And again, because tan theta is a negative number divided by a positive number, tan theta is now negative. Out of these, within this quadrant, only cosine theta is positive. So we say, as a general form, first quadrant all, second quadrant sine, third quadrant tan, fourth quadrant cos. There's all sorts of mnemonics and like little phrases that people use to remember this thing. But as a general rule of thumb, it's better to remember this as just a quick way of reference and see which values of sine, cosine and tangent are positive, negative within these four quadrants. If you have theta in between 90 degrees and 0 degrees, all of them are positive. If you are between 90 and 180 degrees, only sine is positive. If you are between 180 and 270 degrees, only tan is positive. And if you are between 270 degrees and 360 degrees, only cosine is positive. I hope this is helpful, and you can try to find a mnemonic or some word that you can use. All, sine, tan, cos, in that order anticlockwise. And finally, regarding the graphs of trig functions and their special values. If we consider theta, sine theta, cosine theta and tan theta, the important values which I would recommend you to know, and you should really know if you are going to have some general quick reference to angles, would be the angles 0 degrees or 0 radians. I'll actually write both the radian and degree format. 0 degrees, 0 radians. You should know 90 degrees, pi by 2 radians. You should know in the middle 30 degrees or pi by 6 radians. You should know 60 degrees or pi by 3 radians. And you should know 45 degrees or pi by 4 radians. These ratios should be known to you. Their sine, cosine and tangent values should be known. So, 0 degrees or 0 radians. Sine of 0 is 0, cosine of 0 is 1 and tan of 0 is 0. For 90 degrees, sine of 90 degrees is 1, cosine of 90 degrees is 0 and tan of 90 degrees is approaching infinity. I'm not going to say that it is infinity, because in fact it's plus or minus infinity at that exact point, because remember, it was undefined at that point. The domain was not defined at tan theta, where theta is a multiple of pi by 2 plus some n times 90 degrees. So I'm just going to say approaches infinity, not equal to infinity, approaches infinity. You could even say plus or minus infinity here, but I'm going to say approaches infinity from the negative direction. Next, 30 degrees. Sine of 30 degrees is half. Similarly, cosine of 60 degrees is a half. You will note that this is true, and we can know that this is true easily because 60 degrees is 90 degrees minus 30 degrees. And if you'll recall, sine of 90 minus some angle is cosine of that angle. Cosine of 90 minus some angle is sine of that angle. Here we have 90 minus 30 is 60. 60 minus 90 minus 60 is 30, so it all works out. Similarly, cosine of 30 degrees is root 3 divided by 2. Because of this, sine of 60 degrees is also root 3 divided by 2. And finally, for 45 degrees, the ratios are 1 over root 2 and 1 over root 2. These are important values that you need to know. As for tan, to get tan, you just need to divide sine by cos. Dividing half by 1 root 3 divided by 2 gives you 1 over root 3 here. Doing the same in here, root 3 divided by 2 divided by half gives you root 3. And similarly, 1 over root 2 divided by 1 over root 2 will simply give you 1. We can see this in certain triangles. If we draw a triangle, we can identify clearly what this means. If I draw a 60, 30, 90 triangle like this, what we have here, if this is 30 degrees, this is 90, this is 60 degrees. If we say that this longest length is 2, this length is 1, and this length is root 3, we can see that this is a valid right angle triangle because 1 squared plus root 3 squared is equal to 1 plus 3 is equal to 4 is equal to 2 squared. Therefore, 1 squared plus root 3 squared is equal to 2 squared. We have a valid right angle triangle formula, so this is a valid right angle triangle. Next, considering the ratios. If we take the sine of 30 degrees, sine of 30 degrees would be opposite divided by adjacent, which would be 1 divided by 2 or a half. Clearly we can see that sine of 30 degrees is half as predicted, well, not as predicted, as I stated in this table. Similarly, if you play around with this triangle, you can find the other values also, like tan of 60 degrees would be opposite divided by adjacent. Opposite is root 3, adjacent is 1. So tan of 60 degrees would be root 3 divided by 1 or root 3. The other triangle we want to consider here is the triangle that is such as this. A triangle which is isosceles triangle. Both of these lengths are equal and we have a hypotenuse here. If this length is 1 and this length is 1, then we have that 1 squared plus 1 squared is hypotenuse squared, which is 1 plus 1, which is 2. So whatever this number is, let's call it a. A squared is equal to 2, which then means that a is root 2. So we have the triangle 1, 1 and root 2, where these two angles here are 45 degrees and 45 degrees. So here we can see sine of theta is 1 over root 2. Cosine of theta is also 1 over root 2. So we can see nicely the symmetry here, and we can also see tan of theta, tan of 45 is opposite divided by adjacent, which is 1 divided by 1, which is 1. And finally, I will link an animation which clearly shows you this relationship. But for now, I'm just going to graph the three functions and not really explain too much. I will attach a video containing an animation of the sine, cosine and tangent, which will help you better understand how this wave-like form occurs. But for now, the graph of sine, cosine and tangent look like this. If you take this as x, this as y, then sine of x looks like this. If you take 0, it goes like this. It has a relationship which is a very nice smooth curve, and in fact this is the curve often seen in signal generators and even your house's electrical power. The curve of the variation of the current of AC is in fact the sine curve. The sine curve peaks at 1, so this peak value here is 1. It has a negative peak at -1, so this value here is -1. It repeats every 360 degrees, so this is 2 pi radians here. This value here is pi radians. This value here is pi by 2 radians. This value here is 3 pi by 2 radians. I will not be elaborating here. There will be an animation video which I will create and attach. It will be on the top right as a card. You can click it and take a look and understand better the variation of sine theta, cosine theta and tan theta with the angle theta. So this angle, this graph here is y equals sine x. Considering the shape of cosine theta with respect to theta, if we draw the graph, recall that we found sine theta and cosine theta have a relationship. Sine theta is cosine pi by 2 minus theta. This relationship manifests itself by the fact that sine theta and cosine theta have the same shape but are offset by a certain amount. They are offset by 90 degrees. If I draw cosine theta, it will look like this. You'll notice it looks very similar to sine theta, and you're right, it is. It is very similar to sine theta, except for the fact that it's shifted to one side. You can see, if I just cover up the left side here, the remaining portion of the graph of sine theta is exactly the same as the graph of cosine theta. We call them phase shifted relative to each other. Cosine theta is phase shifted 90 degrees relative to sine theta, but they are actually the exact same curve. It's just that they are not aligned with each other. Again, cosine theta varies between -1 and 1 inclusive. At the maximum point, cosine theta is 1 at x equals 0. At the minimum, it's -1 at x equals pi. And similar to sine theta, cosine theta repeats. It repeats at 2 pi radians. And finally, tan theta, which has a very interesting variation. Tan theta starts out at 0 like this, goes up, goes very up, goes up actually to infinity before it reaches 90 degrees here, which I'm having trouble in drawing. It goes towards infinity before reaching 90 degrees, which is pi by 2 radians. And on the right side of the 90 degrees, it comes from negative infinity, goes up, goes through 0, such as this, and emerges from the other side to repeat it again. Goes up like this, again not passing that point, going to infinity, again coming up like this and continuing the cycle. This is pi by 2, this is 0 over here, this is pi, this is 3 pi by 2, and so on. It is repeating itself. If we take this point here and this point here, tan theta is repeating itself instead of every 2 pi radians, every pi radians. It's repeating itself twice as often as the other two trigonometric functions. In terms of special values, tan theta can go to plus infinity and minus infinity, but it has a special value at pi by 4 and 3 pi by 4 and such. At pi by 4, it's equal to 1. At 3 pi by 4, it's equal to -1. It also has the negative symmetry of negative tan theta being equal to tan negative theta, as you may recall, and it repeats itself every pi radians. If you haven't watched the video that I have linked, watch it. I highly recommend it. It's a nice animation to show you how these three functions vary when you consider increasing or decreasing the angle theta. And after this, there's one more section we need to discuss. It is the inverse trigonometric functions. I actually mentioned these in a previous video where I talked about functions that are not actually proper functions. You can define an inverse that will work, but it will not work as a proper inverse function because it will not give all the values of your complete output. So what I mean by this is, if we consider the sine function here, y equals sine x. Give me a second, I'll actually label this as y equals cos x. Considering y equals sine x, for a single value of y, there are multiple values of x. This means that if we try to make an inverse function, we would have multiple possible outputs and it wouldn't work as a proper inverse function. Over here, for let's say this is half, 1 over 2, there are multiple outputs that will give you, so multiple inputs of the original function sine x, that would give you sine x equals half. Because of that, a proper sine inverse function cannot be easily made. Instead, what mathematicians do is limit the values of sine to a certain range. I actually talked about this in that functions video. We limit the values of sine x between -90 degrees and 90 degrees. And within this small range, sine x is 1 to 1 with all the values of x from here to here. And then we use that little format, this little area, to find our inverse functions, inverse sine functions. We do a similar thing for cosine. For cosine, we take this range here from 0 up to pi radians. We take this range and we use the inverse function for that. Similarly for tan, we take the range of, if I extend this in this direction, negative pi by 2 to pi by 2 for our range of tan. So here, if we draw the graphs of the inverse functions, we will see a little issue. Considering sine inverse x, Sine inverse x is only defined in between -1 and 1. So its domain is the values from -1 to 1. To be expected, since the range of sine x was -1 to 1. However, the range of sine inverse x is equal to -π/2 up to π/2. We are limited. We do not have values outside of this range. If we want a value outside of this range, we need to do some addition or subtraction of π/2s or pi's in order to get to that location. If I draw the graph of xy, sine inverse x would look something like this. And if I mark some special values on this graph, the special values would be something like -1 giving -π/2, 1 giving π/2, 0 of course giving 0, and let's see what else. Well, if we had half here, if we had 1/2 here, a half would correspond to 90 degrees of π/6. Similarly, -half would correspond to -π/6, like so. So here -half would correspond to that, and so on. If we consider sine of pi, you will recall from above that sine of pi was 0. Sine of pi was 0. However, if I take the sine inverse of this value, I will not get pi. Sine of pi is 0, but sine inverse of 0 would be 0. So we get sine inverse of 0 is 0, meaning sine inverse of sine pi not equal to pi. So this is what I mean by it does not follow the proper inverse function rules. You will recall, for a proper inverse function, we have the property f of f inverse of x equals x, and f inverse of fx also equals x. These two properties are not withheld by this formula, so therefore this is not a proper inverse function. It is a limited inverse function. Similarly, if we consider cos, the cosine function is also limited between two values of 0 up to pi. We do not have any values outside of here. If I draw the graph of cos inverse x, which I'm going to do, and I know that the x-axis needs to be down here, so I'm going to draw it like that. If I draw like this, x, y, cos inverse x would look something like this. Something like that. So at this point, x equals 1 would give us 0. X equals 0 would give us pi/2. And x equals -1 would give us pi. This is the graph of cos inverse x. Again, cos inverse x does not have the same, it has the same exact problem as sine inverse x does. It is not a proper inverse function. It does have some values. For example, if I put a half into here, a half would give us pi/3 over here. So it doesn't actually line up the way I've drawn the graph. I'm actually going to erase the graph a little bit, try and make it line up properly. There, that's better. Right. So at half, pi/3 and all of that. But if we take, for example, cosine of some angle outside of the range, let's say if we take cosine of 2π, cosine of 2π will give us 1, but cos inverse of 1 will not give us 2π. If we consider the graph here, cosine of 2π gives us 1, but cos inverse of 1 does not give us 2π. Cos inverse of 1 actually gives us 0 degrees. So in that case, this is 0, which means that cos inverse of cos 2π is not equal to 2π. So we have an issue where the inverse function does not produce the proper inverse. We have instead a limited inverse function. It does not have the property f inverse of fx equals x. This property is missing here, which means this is not a proper inverse function. However, if we draw the graph of tan inverse x, it will look something like this. Tan inverse x will be something like this on this side. Similarly, something like that on that side, where we are approaching a value of pi by 2 here, and we are approaching a value of negative pi by 2 here. Negative pi by 2 here. So here what's happening is, as you input a very large x, you get an sine inverse or tan inverse function will give you an answer very close to pi by 2. But recall that since pi by 2 is not in the domain of tan x, pi by 2 could not be in the range of tan inverse x. In fact, in the limit as x approaches infinity, tan inverse x will be pi by 2. However, that will not happen for any finite x. So we can say this right here is an asymptote. The tan inverse function will never reach the level of pi by 2. Some special numbers here of course are 1. 1 here will output pi by 4. Similarly, negative 1. Negative 1 will output negative pi by 4. Other than that, there's not really all that many special values. You could do pi by 6 and pi by 3 here, and that will give you something. Pi by 6 here and pi by 3 here will give you these. Pi by 6 gives you 1 over root 3, and pi by 3 gives you root 3 over here, root 3. Other than that, there's not really all that much to talk about this tan inverse function. So that would be it for our lesson. Remember that sine, cos and tan inverses are not proper functions, which means if you have sine of sine inverse x, you cannot write this directly as x. Sine inverse of sine x, not necessarily equal to x. However, sine of sine inverse x equal to x if x is between negative 1 and 1. This is valid. You can do this. This one, no one will have a problem if you do this. Sine of sine inverse x is x if x is between negative 1 and 1. However, be cautious when you see sine inverse of sine of some value. It is not necessarily equal to that value. It would be equal to that value if x is in that given range. For sine x, sine inverse x is defined as a domain of negative 1 to 1, but a range domain of inclusive negative 1 to 1, and a range of negative pi by 2 to pi by 2. So, because of this, if x is an element of, I should say here also I made a mistake. Here this is not an equal sign. This should be an element of sign. Similarly here, if x is in between negative pi by 2 to pi by 2, in this particular case, then sine inverse of sine x is actually equal to x, because within that range we have a one-to-one correspondence between sine x and sine inverse x's values. Similarly, for cos inverse x, the correspondent range is 0 to pi. What this means is that cos inverse of cos x equals x if x is an element of the set 0 to pi. And lastly, for the tan case, tan has the range, tan x has the range going from negative pi by 2 to pi by 2, in which case tan inverse of tan x equal to x if x is an element of the set negative pi by 2 to pi by 2. So as a final note, if you really want to write that tan inverse of tan x or sine inverse of sine x or cos inverse of cos x is equal to x, make sure that the value of x is within these relevant ranges. This will be the final note within this lesson, and with that we will conclude this lesson for today. Thank you for watching and goodbye.